In this section, we will look at analysing the data from our experimental design and drawing conclusions. We're going to follow the following analysis procedure. We're going to identify the influence that each factor and interaction has on the response. We're going to plot that on a graph, and from this we're going to develop an empirical model. Now, in normal practice you would also perform statistical testing, but this is beyond the level of this introduction, so we will omit that for the moment. We will then draw conclusions and perform confirmatory experiments. In order to assess the influence that each factor has on the response, we will calculate the effect. So we're going to calculate the A effect, the B effect, and the AB interaction effect. Now, this may look like a horrendous equation, but in actual fact it's not. This means that the influence that factor A has on the response is determined by the average response when factor A is set high, minus the average response when factor A is set low. The bar on top essentially means the average. Similarly, the B effect is equal to the average response when factor B is high, minus the average response when factor B is low. And we can also determine our interaction effect. Generally, this information is displayed on an effects plot. In relation to our Statapult, factor A is our stop position and factor B is our angle. Here we see the interaction, and the AB interaction refers to the interaction between the stop position and the start angle. Let's calculate the influence of factor B, in other words, the angle. If we take the average response when A is high, it's 240 and 310. Here we see 240 and 310. So we add these together and divide by 2 in order to get the average. And from that we subtract the average response when the start angle is low. This is the sum of 160 and 230, and divide by 2 in order to get the average. So we're subtracting 195 from 275, giving us an effect of 80. What this means is that the start angle has an influence of 80 on the response, or the distance. So as we move from 160 degrees to 170 degrees, the average distance increases by 80 centimeters. If we take the influence of the stop position, or the A effect, when the average response when A is high is 230 plus 310, 2 minus the average response when A is low, which is 160, and 240. Summed together and divided by 2. This gives us 270 minus 200 equal to 70. So this means that as we move from stop position 2 to stop position 3, the distance that we achieve increases by 70 centimeters. If we look at the interaction between the start angle and the stop position, the average response when AB is high is 160 plus 310 divided by 2 minus 230 plus 240 divided by 2. So in actual fact it's 235 minus 235 equaling 0. So in this experiment there is no interaction between stop position and angle. Now, as we identified earlier, we would like to show this graphically. See here that as we move from the stop position, the low stop position, to the high stop position, our response, or our distance, increases by 70. The start angle, if we evaluate at 160 degrees and 170 degrees, the distance goes up by 80. If we plot the interaction plot, here we see the start angle of 160 at the low level, the stop position at the low level. We see this line. When the stop position is at the high level, we see this line being formed. The fact that these lines are parallel indicate that the interaction is not likely to be significant or influential. The more that these lines deviate from being parallel gives us a greater indication of the influence that the interaction may have on our process. The next step is to develop our empirical model. And we see here the empirical model. This is the generic empirical model associated with a two-factor design. Y hat is the predicted response, or predicted output. In the case of the Catapult or Statapult, it's the predicted distance. Mu refers to the overall average. This refers to the overall average of the 4 experiments that we conducted. And we see in the equation the A effect, B effect, and the AB interaction effect. The XA, XB refers to the coded levels of -1 and +1. If we put the values in to this empirical equation that we got as part of our experiment, we conducted 4 experiments. If we add up the results of those 4 experiments and divide by 4 in order to get the average, we get a value of 235. The A effect, or the stop position, had an influence of 70. 70 by 2 is 35. And the start angle had an effect of 80. 80 by 2 divided by 2 is 40. So this represents our empirical equation. Now the empirical equations are very, very useful because they, as well as telling us how our process operates, they allow us to predict how our process will operate should we change the start angle and the stop position. Let's try that now for the moment. We would like to achieve a target distance of 220 centimeters. We can use our empirical equation to achieve this. This will tell us how we should set up our process in order to achieve this distance. We will initially set the stop position, which was factor A, to level 2. This was at the low level, so we replace XA by -1. We can then rewrite the equation. Note in this case, our y hat is 220 because this is the distance that we want to achieve. So we want to achieve a distance of 220 centimeters, and we want to identify how should we set the start angle in order to achieve this distance. So if you note this particular equation here, we can use this equation to identify what our start angle should be in order to achieve a distance of 220 centimeters. So if we rewrite this equation in terms of XB, it means that XB is equal to 20 over 40, which is 0.5. Now we need to relate that back to natural variables. Currently this 0.5 is encoded variables of -1 and +1. But bearing in mind that the -1 referred to an angle of 160 degrees, the +1 referred to an angle of 170. So the 0 position on a number scale would be 165, and the 0.5 position would be 167.5 degrees. Therefore, in order for us to achieve a target distance of 220 centimeters, we should set the start angle to 167.5 degrees and the stop position to position 2. This is all achieved by the empirical equation. Now the empirical equation is an extremely important aspect of experimental design because it may identify settings and levels which we haven't even evaluated in order to achieve the optimum. Our next step is to perform confirmatory experiments at our The next step is to perform confirmatory experiments with our Statapult and see, do we achieve this target distance of 220 centimeters. Coming out of experimental design, we will have performed confirmatory experiments. These will have allowed us to validate the conclusions in the empirical models. Now, it is important to realize that the experimentation is part of a learning process. We're learning more about the process by conducting experiments. In that manner, they should be iterative, so we can find out more information about the process, so that we can conduct experiments that will identify what the levels and factors of the next experiment should be. Our experiments should also be sequential, so that we can combine the results of a number of experiments and analyze them as a whole. Experimentation is a continuous process, and we should not apply all the resources that have been provided to us on the first experiment. We may need to refine the models and revise the experiments as we're going along. This concludes part C of lecture 5, where we analysed the DOE and we drew conclusions from the experiment.